Okay, good morning. So, we will have a midterm on Friday. Please study hard. The same format as last time, and one fewer question than last time. The problems are, the syllabus of the exam is already posted on Brightspace. I think I also typed a couple comments in Piazza last night or the day before, because there are questions about, in the past exam, there are problems that doesn't seem to be covered in the semester. So I explicitly mentioned what topics would not be asked. So you can look at the Piazza comment. Basically, I'm looking for some very basic understanding of transformation of a random variable, okay? Transformation of random variable. I'm looking for some very basic understanding of this conditional expectation. I'm looking for some really basic understanding of if you have two random variables, if you want to sum them up, how do you do the calculation, okay? They are not tricky at all. Very straightforward, not tricky, just do your study, okay? So that's the promise for the exam. So what I want to do today is to talk about these two sections together, some of two random variables with many examples. The bottom line is that when you have random variables x and y, when you sum them up, it's going to become the convolution of the two PDFs. That's the principle. Okay? Eventually, we want to show that. And then we want to show some examples. Now, these two set of slides, I want to sort of blend them together by talking about the examples. So let's go with them one by one. So here's the first example. You have the first distribution, x. You have the second distribution, y. Okay? And then you want to look at x plus y. And I did some super messy calculation last time, which turns out to be correct. It just is super messy, super messy. So I'm going to tell you an alternative solution approach that's a little bit more manageable. If you continue what I did last time, if you are patient enough to go through all these tedious things, you will actually get to the answer. I verified that. Okay. All right, but let's don't waste the time on there. Let's look at this problem from another angle. So when you have this x plus y, okay, x plus y, now the principle is still true, right? Because eventually, if you want to find the PDF of x plus y, then you want to find the CDF of this random variable z, which is x plus y. To find the CDF of z, you want to find the probability. So these are still the valid approach. The thing that I think it is a better approach to do is that let's don't look at these two specific distributions too early, okay? For some reasons I'm going to tell you. So let's start with two distributions. So you have a z equals to x plus y. So that's the definition, right? And I want to find the CDF of z, which is the probability of z less than the small z. And this is going to be the probability of x plus y less than z. Okay, so now I'm going to do some calculations, and eventually I will get some expression down there. Then I'm going to calculate the PDF. The PDF, of course, is just going to be the derivative of the CDF. So that's coming from the definition. And then I'm going to do some additional calculation and then find the final result for you, right? So we just need to fill out these blanks. Now, let's look at the first half. How do we find this probability? And my comment is that please do not look at the individual distributions, because if you look at the individual distributions, you run into the mess that I had on Monday, okay? Just because when you look at each individual distribution, you need to take care of the range, you need to look at the formula, those will run into big mess. Okay. However, there are some basic principles that will apply for all distributions. Let's work on those first, and then we can plug in the specific formulas later on. So what would be a generic formula? Well, the generic formula here is that you want to calculate the probability of this pair of random variables, and by definition of this problem, they're independent, which is a good deal. So what do I mean? Well, you need to integrate this joint distribution of x, y, dx, and dy over a set. The set is that x plus y is less than z. Okay, so that is the definition of this probability, regardless of what specific PDF of fx and fy they are. Okay, regardless what fx and fy they are. Just for any fx and any fy, that will be the formula. And by independence, this can be written as fx times fy. So you can factorize your joint into the individual distributions. So this is still valid for any distribution fx and fy. So there's nothing crazy here. Now, the next step is also valid for any fx and fy, not particular for these two distributions, which is how do you calculate this integration for this range? How do you calculate the distribution for this range, integral for this range? Now, for this range, we know that there's a chart, right? So there's a diagram. There is x-axis and there's a y-axis. I want to look at this equation, x plus y less than or equals to z. And so that's just equivalent to y less than z minus x. So it will be a line, and we discussed the last time. This is going to be a straight line with a negative slope. The slope is -1. So it has to be something like this. Okay, so that would be the negative slope. And it has to include the origin, because if you put a 0 here, put a 0, you have a positive z, then it will be included, so it will be on this side. Now pay a little bit attention here that because I'm looking at generic fx and fy, it doesn't need to tie to the fx and fy in this problem. My diagram actually starts with -infinity to this line, and from -infinity to this line. Okay. Now, of course, if you plug in the specific distribution, you've got to start with 0. That will cause some mess, just because you can't start with -infinity to infinity. So that will cause some mess. Never mind. So what do we want to calculate? We want to calculate this double integral, right? So this is a double integral over this range. So let's write down the formula. So your double integral, you have this f of x, f of y, dx and dy. Now, whether you want to dx first or dy first, it doesn't matter. We can do both ways. So let's go with dx first. So if we want to do with dx, then you want to go horizontally. Okay? Clearly, the endpoint will be this, and this endpoint will be x equals to z minus y, coming from this formula. Right? So this is the endpoint. So the endpoint will be z minus y. How about the lower limit? The lower limit will be for -infinity. Okay, so you will go from -infinity to z minus y. So that's the horizontal scan. For any specific y, I'm going to run a horizontal scan. And then I'm going to run many horizontal lines from -infinity up to infinity to eliminate all the possible y's. So where would be the range of y? Y will go from really -infinity all the way up to +infinity. So that will be the entire range of y. Okay. Now, again, if you plug into this specific formula, y has to stop at certain fixed number z. And that will, again, create some mess. Okay, so go with -infinity to infinity. So that would be the range of y. Now, look, I still have not yet plugged in my specific distribution. This is true. This statement here is true, okay? From the beginning up to this point, it's true for any fx, any fy, Okay, it's true for any fx, fy. So it's very generic. So now, so that's the answer for this CDF. I haven't plugged in any formula yet, but that is the sort of the general form of the CDF FZ. Okay, so now let's continue with the story here. I want to find the PDF of Z. I want to find the PDF of Z. So the PDF of Z is this. It's the derivative d dz of your fz of z. Okay, and this fz of z is just a double integral from minus infinity to z minus y, and then from minus infinity to infinity, and then you have fx, fy, dx, and dy. Just plug in the definition of your fz to here. Okay, this is still true for any fx and any fy. Still a good thing, right? Generic. So let's move on. And here, now you have this derivative, you have the integral, and I'm going to move this derivative inside, okay, because I'm taking the derivative with respect to z. So I can move inside this, the first integral. So you have this d dz of minus infinity to z minus y of fx, fy, dx, and dy. Okay, and so I'm gonna rearrange the integral by moving this dx inside. So I will have this integral, that's an outer integration of dy, that's a fy, but inside there is a d dz integral from minus infinity to z minus y of fx dx. So I'm just moving around the order of the integration. So once I do that, then we can apply a very useful formula, and that's called the fundamental theorem of calculus. And let's see how we can do it. So this thing here, this is a derivative followed by an integral. The derivative followed by integral by the fundamental theorem of calculus, fundamental theorem of calculus. That's going to give me f of z minus y. That's, of course, this is x. Okay, this thing here will be this. Why? Because the fundamental theorem of calculus says that d dz of any integral to any z, and then you have whatever x here, dx, is going to be fz. So that's the theorem. The theorem says this. Now, if I have something else, okay, so now if I have something else, I have d dz of integral minus infinity of z minus y fx dx. That can be written as the chain rule. So you a d of z minus y, and then you do this, z minus y f of x dx times d of z minus y and dz. Okay, so that's just a chain rule that you sort of break this z minus y into two pieces. And this thing here will just follow the fundamental theorem calculus. So that will give you f of z minus y. So that is this half. Now, how about this derivative? This is just 1 for the z minus y. Okay, so that one comes from chain rule. Okay, so now once we have this result, then we can continue with the calculation here. The calculation will give me equals to integration from minus infinity to infinity of this fx. Here is z minus y, and then y of y dy. Okay, so you do all the way to here, then you have this, the PDF will become this integration from minus infinity to infinity of this fx of z minus y and fy of y. Okay, this is what? Integration of two functions, flipped, shifting, add, and it's called convolution. Okay, so now this result again is valid for any fx, any fy. Okay? Any fx, any fy. Not just for this particular problem. Still at this point, I haven't plugged in that particular formula. Okay? Up to this point. Good. So now let's move on and talk about how do we plug in these two formulas. Okay, so now we can plug in these two formulas. If you want to find, so this is fz of z. You want to plug in these two formulas, that's not too bad. So you have fz of z here. If we integral, okay, and then you have fx. So fx evaluated at the z minus y, so you have a z minus y of e to the power z minus y. So that's fx. Fy, you have ye minus y, and then dy. Okay, so life is good so far. How about the integral? Now, where should be the lower limit and the upper limit? Now, that we need to think about. Okay, here, this formula is true for any fx, any fy. Now, once I plug in the fx and fy, then the upper and lower limit has to be, we think about. Okay, we think about. So what should be the range of y? Okay, so now you're integrating with respect to y. You need to think about y. So here, let's look at this. This is your z minus y, right? And this z minus y has to be part of your x. Okay, so here you have this thing of z minus y, and this z minus y is actually your x. Your x has to be bigger than 0. According to the problem definition, your x is bigger than 0, right? For any x to be valid. So your z minus y has to be bigger than 0. So that means if I want to look at y has to be upper bound by z. There's a lower bound by the other problem, so you have y bigger than or equals to 0. So figure out the range. The range is from 0 to z, which is also true if I look at the diagram, right? You look at a triangle, the y has to go from 0 to z. So that's okay. So now let's carry on the calculus. So this is from 0 to z, and then you have this product. So you have z y minus y squared, and then you have what? E to the power minus z, and then e to the power y times e to the power minus y, so they cancel. Okay, so now you have this integral, and then you have e minus z coming out, and then the integral would just be z times y squared divided by 2 minus y cubed divided by 3 z and 0. I hope I'm right. That's the integral. And then let's do the calculation. So you plug in the z to the y here. So you have z cubed divided by 2 minus z cubed divided by 3. The other one would be 0. So you have z cubed divided by 6 times e minus z. Good. And this is for z bigger than or equals to 0. Okay. Right. So we found the PDF of z. Now there is the other range. If z is less than 0, then of course your fz is 0, right? Because that you don't have anything to integrate. So why is this approach a little bit better, in my opinion? Because you work all the way to this point, it's still the generic definition. It applies for all the fx and fy. The moment you plug in your fx and fy, it will be already one fewer integral. Now, why was it so messy, although I was right? Is because when you plug in the specific formula up here, you have a double integral to worry about. And then you integrate so hard then you take the derivative and you eliminate one integral. So it's like you spend a lot of time working on things and then you just eliminate your effort. So that's the problem. And because you're doing this double integration, you spend so much time and it's tedious. Double integration is always very tedious. And you need to integrate for both x and y, and eventually you want to eliminate one of those, right? So that's the problem. Now, if you go with this approach, the derivative by the fundamental theorem calculus is already taken care of, right? So when you should do this calculation, one integral is killed. So you have one less thing to worry about. You just need to figure out the range of y. So that's a little bit easier. If you're patient, okay, which is not me, you're patient, you carry on the calculation and finish the last time, just patient. Or, okay, I find out one way, is that you go to Google, you type, what do they call symbolic integral? You type it, okay, you type it, and then you type in this formula, it will do the calculation for you, and it's pretty long. I figure out I was right, it's just pretty long. And then just sit down and do the derivative, you'll get it, okay? But if you go with this approach, it will be a lot easier. You see that you do this calculation. So what would be the key points as you are trying to study? I think the key point is to recognize whenever you x and y, okay, whatever you do, you have to land on this formula. It's just the convolution between x and y. And then the rest is to figure out the range. Once you find out the range, it's just calculus. It's just calculus, okay? So let me give you one more example. Let me give you one more example just to make sure that we are all on the same page. So the following example is this. It's not example number 2, but something I have in mind. So let's do this. You have, let's consider fx to be a Gaussian. Okay, 0 means Gaussian. So you have 2 pi sigma square e x square divided by 2 sigma square. It's just this. Okay, 0 means Gaussian. The mean is 0. And then your fy is 2 powers, okay? -1 and +1. Half and half. How about that? Okay. So I want to find x plus y. So z equals to x plus y. So what is f z of z? Okay, so how should we do it? Now, first of all, let's spend some time to write down this PDF of y. What is the PDF of y? The PDF of y for this thing here. Any suggestions? Yes. X plus 1, and then? Plus half of delta x minus 1. Okay, great, good. Okay, so this is the PDF of not x. Come on, it's y. Yeah, y. Okay. All right, so we have this. Okay. Now let's find the the PDF. So to start with, I will not try to remember the formula because I'm such a bad person to remember things. So I will start with from scratch. I will still try to find out fz of z, which is the probability of x plus y less than the z. Okay, it's still the same thing, regardless of what distribution I have. And then I have this double integration of x plus y less than z. And then I have f x of x, and then I have y dx and dy. I still have this, right? And then I still need to draw this diagram, and because this is generic, I still need to integrate from minus infinity to infinity. Now, here's the deal. If you don't do this generic approach, you're going to cry because your x is defined, okay? But then your y, you only have 2 pulses. How are you going to look at things? Wait, you see my point? There are only two delta functions. Where should be the range of y? That's already very tricky. So if you don't start with a generic formula, it will just be very hard to calculate this double integral. But if you start with the generic formula, you know that, okay, this is generic formula, so that you have fx, you have fy, dx, and dy. X will go from, again, from here to here. It will be from minus infinity all the way to z minus y. And then here from minus infinity to plus infinity. Well, exact same formula as before, which is good. And then you do a ddz, which is going to give you the PDF of your fz of z. So this is going to be the integral minus infinity to infinity, minus infinity to z minus y. Again, fx, fy, dx, and dy. Well, exactly the same procedure, right? So you can imagine what will happen if I apply the fundamental theorem calculus. So that will give you minus infinity to infinity of my fx of z minus y. So my number can go in, and then fy of y dy. Come on, I just derived the convolution formula again. Okay, so the second time in this lecture. You see, it's not that hard. Okay, so that's true for any generic result, any generic fx and fy. And now what should I do here? Well, I need to plug in the fx and fy. So, so let's do it. So fx would just be 1 over root 2 pi sigma square, right? And then e minus x, not x, it will be z minus y squared divided by 2 sigma square. Fy will be 1/2 delta of y minus 1 plus 1/2 delta of y plus 1. Okay, and dy. It's a little bit long, but not too bad. Okay. So what should we do here? You have an integral that involves a Gaussian, and then you have a delta. What should we do here? So let's do them one by one. So you have 2 integrals, right? Integration 1, integration 2, minus infinity to infinity, 1 over root 2 pi sigma square e minus z minus y squared divided by 2 sigma square, delta of y minus 1 dy. That's a 1/2. There's another 1/2. Okay, so I will do the rest later on. Just look at this integral. This integral is what? Any suggestion here? Yeah, you want to try? Huh? It's not 0, unfortunately, yes. Y equals to 1. Plug y equals to 1 into this Gaussian, okay? Plug this y equals to 1 into Gaussian. Do you agree? Okay, so let's do it. So plug y equals to 1, right? Y equals to 1 into this Gaussian. So you have 1/2 sigma square, 1/2, right? E to the power minus z minus 1 square divided by 2 sigma square. Plug the 1 into the y. Okay, good. How about the other guy? The other guy is 1 over root 2 pi sigma square e minus z minus y square divided by 2 sigma square. And there's a delta of y plus 1 dy. Now, this time, what should I plug in? Minus 1, okay? So plug y equals to minus 1 into this thing here. So you have 1/2, that's root 2 pi sigma square, e minus z plus 1 square divided by 2 sigma square. Good deal. Okay? It looks really complicated, but let me show you why it is very simple. Let's draw it out. Okay, let's draw it out. Okay, so here is your z. Okay? Everything is in z. This is your fz of z. This is axis of z. Ignore the 1/2, ignore this part. Just look at this. What is this guy? Can anyone describe the shape of this function? Yes? Gaussian, where is it centered? 1. Okay, so let's put a 1 here. Let's draw Gaussian. Okay, the variance is sigma. How about the other guy? Of course, it's -1. Of course, you have this. Okay, so if it's the Gaussian. And then 1/2 and 1/2, right? So they have equal importance. So the two Gaussians will have the same height. And now when you add them up, then you need to have some imagination, right? There's some overlap here. Depending on how big a sigma is, then it's going to give you something like this. Do it. This is your fz of z. Okay, and the peak is -1. The peak is +1. Now, if your sigma is really, really big, then they will, the two will become closer. Not the center location, but then this value will go up. Okay, if your sigma is really, really big. If your sigma is really, really small, then you can see the two pulses more clearly. This is exactly what I mean by convolution. You start with two pulses, one at -1, one at +1. You convolve with a Gaussian. Just move this Gaussian, slide from the left to the right. Then you can build a mountain here, another mountain there. Right? So that's what I mean by summing two PDFs. So you can imagine in this problem, you have a Bernoulli, and then you have a Gaussian, you convolve them. You say that there are two random variables, x plus y. A Gaussian and Bernoulli, you sum them up, you get another random variable called z. That would be the shape of this z. Does that make sense to you? Okay. Never ever try to add fx and fy. Okay. Some years ago, I had people saying that, oh, what is fz? It would just be fx plus fy. Some years ago. Okay, I hope I wouldn't see it again. That's not true. Whenever you have x plus y in the random variable, you're going to get convolution in the PDF. All right, good. Ready for another example? Let's do more example. I think example will be good. Okay, so how about this example? Example number 2. You have random variable x and y, they're independent. This is fx, this is fy. Oh, this is f of x times y. Now, promise it won't show up in the exam, but I want to show you how to do x times y. Okay, so how do you do x times y? So what would be the principle? The principle is the same. The same principle. It's just not convolution, ladies and gentlemen. It's not convolution, but it's the same principle. How do you find fz, the CDF? Well, the CDF is the probability of x times y less than z. Now, why x times y? The problem asks you to do x times y. Okay? Okay, so you have x times y less than z. How do I do this probability? Oh, double integral fx, fy, dx, dy of x times y less than z. Same deal, okay? Nothing crazy. Then you want to calculate this integral. Now, how do we calculate this integral? Well, you draw the diagram. Okay, this is generic for any fx, any fy. Now, how does this function look like? This is y, this is x. Oh, that's a good question. Y, well, x times y equals to z. That translates to y equals to z divided by x. Okay, z divided by x. So I really hate symbol. Okay, so let's don't worry about the symbol. Let's just think about this. How do you draw y equals to 1 over x? You put z equals to 1. That's a little bit easier for me. How does this function look like? Going down, right? Going down. Okay. Going down like this. Going down like this. Okay, good. So if it goes down, then where should I be integrating? Well, the integration has to go from here. Right? It has to go from here to here. Let me make sure that I have the right result. Okay, so from here to here and then here, from this point. Okay, it will be from minus infinity all the way to this point. Now this point is y equals to z over x. So you have z over x. Okay, and then your y has to go from minus infinity to plus infinity. Okay, so this is fx, fy, dx, dy. So from minus infinity to infinity. Okay. Oh, probably not minus infinity. I think it cannot go below 0. Am I right? Yeah, I don't think you can go below 0. So you have to go from 0 to infinity, from 0 to infinity. Otherwise, I think you're going to mess up because the x can go from minus infinity, okay? But then the y, you look at the start. Well, let's just keep life simple. So start from 0 to z over x, from 0 to infinity. Because otherwise, it's not like that curve, right? That can go from minus infinity to infinity. Here, once you hit the 0, you're integrating the x from minus infinity to infinity. You see that it's converging to 0. You will never have stuff down there. Otherwise, if you want to integrate, it will just be infinity. Okay? If you integrate from here to here, you will get an infinity. So that's not a definite integral. Okay, so we go from 0 to z over x, 0 to infinity. But that's okay. What we cared about is not this. What we cared about is just the generic formula, which is fz of z is d dz of fz of z. And if I cared about this, then it would just be a d dz of this double integral from 0 to infinity, and then from 0 to z over x. And then there's a fx, there's a fy, dx and dy. Okay. And now, we can rewrite this integration, the order. So you have d dz of integration from 0 to z over x. Why am I typing x? Why don't you tell me I make a mistake? This is x equals to z over y, right? Okay. I'm still awake. Are you guys? You should tell me. Okay. Just bear in mind that I'm not very good in bookkeeping these symbols. Okay. So this is fx and dx. Okay, and then there's a fy dy. Okay. Sure, 0. Maybe we can keep it from minus infinity to just make the symbols more consistent, okay, with whatever, okay, with whatever. Make it consistent. My point is that it doesn't really matter. Ultimately, what matters is that the moment you plug in the number, things that you do in the middle, it's okay. All right. So so do this integral. So you're minus infinity to infinity. And then you have this integration. Now, let's see what do I do with this integration. you have fx, and then fundamental theorem calculus will tell you this is going to be z over y, and this is x, right? And now I also have chain rule. Chain rule says that I need to take derivative d of z over y and dz. So there's a chain rule that goes into this thing here. And then there's fy of y, dy. Now what is this? This is just the integration of 1 over y, and then fx z over y, and then fy of y dy. Okay, wonderful. So I have this result. Okay, so I still haven't plugged in the formula, but I do have my integral, which is great. So let's see, what do I have here? My problem is fx is 2x. Okay, so fz of z is, that's an integral, y, and then fx is 2x. So I have 2 of z divided by y. Fy is 1, and dy. Great, so I just plug in the result over here. Now I need to plug in the range. So that would be the moment that we need to worry about the range. So how should I calculate the range? Well, the range is really specified by here. So you have x equals to z over y. And I know by my problem that, where's my problem? The problem is here. My x is between 0 and 1. So that means this is less than 1, this is bigger than 0. In other words, I can write it as z less than y for this half. Okay, z is less than y for this half. And I also know that y is less than 1, so it will be less than 1. So the range that I should put in for this y will be from z to 1. Okay, if I'm just looking at this ratio is your x is between 0 and 1, then you can figure out the range for your y. Now, once you figure out this, then the remaining is just calculus. So you have integration from z to 1, and you have 2 times z over y squared dy. And if you do it right, let me just look at my result here. You will get 2 times 1 minus z, where your z is bigger than or equals to 0. Okay, so this is your, from here to the final result, this is just calculus. Right? It will be 2 times the 1 over y squared. So that we know how to integrate. So we get this result, and we have solved the problem. We solved the problem. One thing to pay attention is that when you are taking the product of 2 random variables, is not the convolution, right? If you look at the result here, if you have x times y, then fz of z is the integration of 1 over y times fx of z over y times fy of y dy. It is not convolution. It's like a scaled version of x times fx, and then there's another scalar that goes out. So that is the generic result for any x times y. Now you can do the same thing for x divided by y. You can do the same thing for x minus y, and so on. So that's addition, subtraction, multiplication, division, so 4 operations. Same principle. Go through the CDF and then go through the PDF, you can get the results. Now, you may not need these in any near future for your work, not for this course, but for actual engineering work. maybe later. Maybe later when you try to deal with more complex events. For example, in my work, I need to deal with x minus y sometimes. You have one measurement, you have the other measurement, you want to subtract. Another scenario will be wavelets. If you know anything about wavelet transforms, so Fourier transform is one. There is another thing called wavelet transforms. Usually when you do wavelet transforms, you do one signal, you subtract the other signal. So once you have the subtraction, you have x minus y. And since I do image processing, most of the time I deal with Gaussians. So if one Gaussian minus the other Gaussian. In many cases, I deal with Poisson. So I have one Poisson minus the other Poisson. So when you take the difference, then you need to go through this kind of procedure to derive the new PDF. So you need that. I promise you will need that, but not today, okay? Not even in this course, but later on in your career, you may need to encounter those. There's a good news, though. Remember there is when you have two random variables, when you sum them, the PDF, it will be convolution. If convolution is too hard, there's an alternative. It's called a multiplication in Fourier domain. So there's a topic called the moment generating function or characteristic function that is really just the Fourier transform of your PDF. And once you're in the Fourier domain, you can multiply the two moment generating functions. Then you take the inverse transform. Usually those are done by the table. So that can help you solve some of the difficult problems. So we can talk about that later. There is one more example that I don't think we have time to go through it. Is again a summation of two random variables. This is very useful. We can comment more on that later on when we talk about the moment generating functions. So you have random variable x1 and x2. They're two different Gaussians. Then the sum of these two random variables, the new random variable, will remain to be a Gaussian. You're just adding the mean, you're just adding the variance. So whenever you have Gaussians, no matter how many Gaussians you have, add them together, they will remain as a Gaussian. So that's a very beautiful result. You can prove it by this convolution. Basically, that tells you another thing. You convolve two Gaussians, you will remain a Gaussian. So that's a beauty. The results, when you go to this, the first line of this slide is the convolution. The remaining, okay. The remaining is very, very long. Very, very long. But they are just calculus. The technique that you're learning here is called this. This is a technique. It's called completing square. It's just tedious. But once you sit down, you go through all these calculations, you can find out the results. So that I'm not going to go through it because we have a much easier proof when we talk about the moment generating function. Okay? All right, so on Friday, please come a little bit early. We will have just the same setup as last time for the midterm. And please study for the few topics I talk about. And wish you good luck. Okay?